Hi, I'm Ozan Unal, and I'll be presenting our work, Discwise Active Learning for LiDAR Semantic Segmentation. We begin by defining the task of active learning, where the goal is to intelligently label a dataset under a fixed budget while maximizing performance. A typical active learning pipeline follows 3 steps, starting with a small amount of randomly labeled data. A model is trained, frozen, and then used to estimate the uncertainty of the unlabeled set. This uncertainty is aggregated over each data unit, which is then labeled by a human expert. These steps can be followed in active learning research for LiDAR semantic segmentation as well, where first a model is trained on a small amount of labeled data, then the trained model is used to estimate the point-wise uncertainty. The uncertainty is aggregated over each frame, and finally the frame with the highest uncertainty is labeled. While this may seem appropriate at face value, the weakness of such an approach becomes apparent when we understand how LiDAR sequences are labeled in practice. Here, the key word is sequences. By projecting each frame onto a global coordinate system, we can form a dense representation of the LiDAR sequence and label it directly. With sequential labeling, we would only need to label a region once in global coordinates to have it labeled on all individual frames. This severely reduces the cost of labeling and is essential for any dataset construction. However, current active learning approaches for LiDAR semantic segmentation do not align well with this established technique for annotating. Thus, we need to design one from the ground up. Similar to any active learning pipeline, we start by training a model with a small set of labeled data. We then estimate the point-wise uncertainty following techniques in Bayesian active learning by disagreement. Here, we decompose the probability of the label y into the integral over all possible model weights. Since the posterior distribution of the model weights given the dataset is intractable, we approximate it using Monte Carlo integration, and simulate variations in the model weights by employing dropout layers within our model and then keeping them active during inference. The point-wise uncertainty can then be captured in a metric such as the mutual information. Having point-wise uncertainty estimates, the next goal is to aggregate it over each data unit. The data unit is what we wish to label, thus it must respect sequential labeling. To also remain comparable to previous approaches, we propose labeling disks. In other words, the region a single frame covers in global coordinates. When aggregating point-wise uncertainty over a disk, we need to be careful of the fact that local point densities change due to variations in the eco-vehicle velocity. A stationary sensor will continue to accumulate more and more points in the same region, which can bias the aggregate. We therefore propose a simple but effective two-step solution, where first, we combat such density variations by aggregating over coarse voxels via a symmetric function, and only then aggregating over a disk via the sum. Finally, we can choose to label the disk with the highest uncertainty and thus complete our framework. However, there are a lot of fixed costs associated with active learning, from training the model to setting up a labeling pipeline. To reduce the impact of these fixed costs, a common approach is to label multiple data units, or disks, every iteration. The issue is disks can intersect in global coordinates. The intersecting regions do not provide any additional information, and disallowing intersecting would not yield an optimal solution. What would yield an optimal solution is our proposed mixed integer linear program that directly maximizes the total information within the union of the disks. Combined, we construct our final pipeline, dial. With dial, we demonstrate 2 key insights. First, when comparing the current active learning approaches on time spent labeling rather than the number of points labeled, we show that sequential labeling is essential for any active learning framework. Furthermore, even if we adapt previous state-of-the-art methods with sequential labeling, our proposed strategy performs significantly better, illustrating that an active learning framework must be built around this core technique. We ablate our components showing the effectiveness of the two-step aggregation strategy, comparing sequential and frame-wise labeling at really low annotation budgets to further illustrate the need for sequential labeling, widely used uncertainty metrics to demonstrate the advantage of mutual information, and illustrating the benefits of our mixed integer optimization-based disk selection strategy. Finally, we incorporate a mean teacher setup to fully utilize all points within the dataset to further improve the final model performance. Observations from the quantitative results can be visualized with the qualitative results, where we observe better tail class segmentation compared to baseline greedy approaches. To sum up, in this work we tackle the task of active learning for LiDAR semantic segmentation, and propose a disk-wise approach that not only achieves robustness against local point density changes in global coordinates, but also directly optimizes the selection of the disks while allowing intersections. Thanks for listening, and make sure to check out our paper with the QR link on screen.